So hi, Frank.
Yeah, thank you.
Good. We start again. It is a pleasure to have with us today Professor Anthony Brown from Leiden University, a person that has been involved in the Gaia mission since '97, chairs the Gaia Data Processing and Analysis Consortium, and he will review for us, highlight some interesting topics of Gaia and give also the perspectives for the future about the Gaia near infrared that will follow. So, Professor Brown, please go ahead.
All right, thanks. Thanks for the introduction and for having me here today. Yeah, so let me just get a couple of things out of the way. Yeah. Okay, so I will talk about 10.5 years of surveying the Milky Way and beyond. And the 10.5 in the title comes from that's the exact amount of time that Gaia has been collecting data before the mission ended earlier this year. And I've chosen to focus on the following topics. So first a quick introduction and then a look back basically at the impact that Gaia has had so far. So this is not necessarily lots of new scientific results from the recent literature, but really looking at the areas where Gaia has had a large impact on astronomy through a few examples. I'll say something about the Gaia survey selection function tools. This is based on a project that I have led over the past couple of years, and I just wanted to highlight.
Did you share your screen, Anthony? Did you share your
I
screen?
see my.
You should share
Oh,
correctly. Yeah.
I thought it was shared, but I was only simply looking at my own slides. Give me a second. Yeah.
Yeah. Just now it works well, but now it's it's opt out.
Yeah. Let me find the sharing again. There we go. Share. Yes. Okay, now it should be visible.
Yes.
Okay.
Yeah, no, that explains why I was missing some things like video panels, etc. Let me just get the controls out of the way. Okay. Yeah. Okay, I'll just go back to the title slide. So as I mentioned, this is titled 10.5 years of surveying the Milky Way and beyond. The 10.5 coming from the amount of time that we've been collecting data, and I'll get back to that throughout the talk. So what I've chosen to do for this review is to really look back at the impact that Gaia has had so far through a number of examples that highlight the areas where Gaia has really changed the game in astronomy. I'll look at the Gaia survey selection function tools, which is a project that I led over the past couple of years, and I'll discuss what they are and a couple of examples of the kinds of science you can do once you have the selection function in hand. And then I'll spend time on previewing what will come out with Gaia DR4, which is scheduled for the end of next year. Also look ahead quickly at Gaia DR5, which is scheduled for the end of 2030, and then end with a discussion of the future of astrometric surveys, which is the Gaia Near mission. Okay, just as a very quick summary of the Gaia survey itself. So as I guess all of you know, it's a mission that collects astrometry and spectrophotometry for about 2 billion objects in the sky, and also radial velocities and spectra for about 100 million objects. And it's an automated survey, which is complete to about magnitude 21 in the G band. It does its own detection of sources on board, so it's not based on any kind of input list. And because Gaia continuously scans the sky over the course of its mission lifetime, you get a quasi-regular time sampling with, on average, about 140 observations per object spread over these 10 years. So Gaia is also, in that respect, very interesting, has been very interesting for transient science, and of course also for things like variable stars. It was launched at the end of 2013, has been operating for 10.5 years at L2 without any major incidents, I should say. There's a couple of things, of course, that we had in the beginning, such as the stray light and things like the basic angle variation, but all of that we can deal with. And the mission has really been, in many ways, amazingly stable and quiet over those 10.5 years. We've had a couple of data releases already. The recent large data release was Gaia DR3 from June 22. And Gaia DR4 is scheduled for December of 26, so the end of next year, and we will come back to that more extensively during this talk. And then finally, Gaia DR5 is foreseen for the end of 2030, which will be based on the full 10.5 years of extended mission data. Now, just as a reminder of what Gaia delivers, in the first place, an all-sky, complete and very high accuracy star atlas, which is symbolized with this picture of the Big Dipper. And of course, the real change that Gaia has brought is the massive availability of parallax and proper motion data for stars all over the sky. But I think what is also very essential to the success of Gaia is the fact that it also gives you astrophysical information of sources. So we have light curves from the photometry, we have low resolution spectrophotometric measurements in a blue and a red band, and also medium resolution spectroscopy from which we extract the radial velocity, but also information on the chemical composition of the stars. And all of that, of course, leads to exquisite information, all the fundamental data that you need for stars to study them, so their distances, motions, but also their astrophysical properties. So let's have a look then at the impact that this kind of data has had in astronomy, and I go by a couple of examples to just illustrate why Gaia has really revolutionized the area of astronomy over, say, the past 8 years or so, 8 to 10 years. So first of all, we now have, since Gaia DR1, basically, easy availability of fundamental astronomical data. Essentially, for any star in the sky, you can look up what is its distance, what is the photometry of the star. For many cases, we have these low-resolution spectra. For a good fraction, also these RVS spectra, and all of that available from an easy interface with the Gaia archive at the various centers where you can retrieve the data. And I think this is really the big change, is that especially a younger generation of astronomers, for them it's completely natural that if you want to know anything about a star, you just go to the Gaia database and you look it up. So I think this has now basically become completely integrated into our ecosystem, and I certainly couldn't imagine anymore living without this beautiful database. Now, the second impact is simply the fact that we have a very high accuracy star atlas. Just a second, I'm getting something out of the way. Yeah. And this star atlas goes to faint magnitudes, about magnitude 21, and it gives you very precise positions, but also parallaxes and proper motions of stars. And this is important in the example application that you see over here. So down here, you see a nice picture of Arrokoth, a Kuiper Belt object that was visited by the New Horizons mission back in 2019. But in order to go there from after visiting Pluto, they needed to know how to navigate the spacecraft. So to that end, they took space telescope images of Arrokoth. You see a zoom in on the couple of pixels that this object covers in a space telescope image. And of course, you determine the orbit by basically doing astrometry on the object plus all the surrounding stars. But at the time that they were doing this in 2017, they were using two catalogs that were available, astrometric catalogs that gave inconsistent results. And so they asked us to help and provide them already a small pre-release of the Gaia DR2 data because they really needed confidence in the proper motions and parallaxes to make the correct orbital prediction for this object and hence be able to navigate towards it. Now this worked beautifully thanks to the Gaia data, and that's of course evidenced over here in this picture that was taken with New Horizons. And at the same time, what they also did is they wanted to map the object already before actually getting there to make sure, for example, that there isn't, let's say, a ring system or other stuff in the neighborhood that could be dangerous to the spacecraft, and also for planning how to take the images. And that was done by looking at stellar occultation that Arrokoth caused also in 2017, which was observed from Argentina. And thanks again to the very accurate Gaia predictions, they could place telescopes at the relevant positions in the shadow path of this object and already map out the fact that it was clearly not a simple spherical object. And you can see that again in this image over here. And here's another example of what you get if you very precisely can predict where to observe an occultation. This is an occultation of a star by Triton, and because they were able to place the telescope exactly in the middle of the shadow path, during the occultation you then get this central flash, which gives you a lot of information about the atmosphere of the object, basically the light rays being refracted through the atmosphere of Triton, and that allows you to do things like derive the temperature, pressure profile, all without actually visiting the object, but really just doing very precise occultation measurements for which you need this very precise star atlas. Okay, the next is an example that all of you should be very well familiar with, which is namely that Gaia provides data for many stars in the sky. And this also means that you have a very dense sampling of the color magnitude diagram and also of the phase space of our own Milky Way. So the dense sampling of the color magnitude diagram, if you look at stars that are moving in our galactic halo, this was a publication that came out together with Gaia DR2. There were these two sequences that were noticed in the halo stars, a blue and a red sequence. And also on the white dwarf sequence, there was substructure noticed that wasn't seen as clearly before, and in particular this branch over here indicated with the letter Q. And then also a result that came out with DR2 was the fact that if you plot the vertical motions of the stars as a function of their vertical position in the disk, that you can see already in the density distribution in this plane that there is a spiral-like feature, which becomes much clearer if you also color code this by the median azimuthal velocity of the stars. And of course, the interpretations of these features are well known. So this split in the color magnitude diagram along the main sequence in the halo stars eventually led to the discovery of the Gaia Enceladus galaxy, which merged with our own Milky Way about 10 billion years ago, and which was the last significant merger that the Milky Way experienced. The structure on the white dwarf color magnitude diagram can be interpreted in terms of the atmospheric compositions of the white dwarfs. But this particular branch sticking out over here is also very interesting because that's actually a sign that white dwarf interiors crystallize as they cool from their initial hot blue state down to the faint red state. And during that cooling process, at some point, the carbon-oxygen mixture inside crystallizes, releases latent heat, and that leads to this pileup of white dwarfs in the color magnitude diagram. This was something that was predicted 50 years ago, but never really observed convincingly, and this was now discovered then with the Gaia DR2 data. And then finally down here, the so-called phase spiral is a clear indication of ongoing phase mixing, so a recent disturbance to the Milky Way disk. And one of the popular explanations, of course, is that the Sagittarius dwarf galaxy, which passed through our Milky Way disk, actually caused the disturbance. And what we're seeing here is basically everything relaxing back into equilibrium. And you can use the diagrams like this to try to infer, for example, when this interaction happened. And of course, there's many, many complications behind all of that. But again, it's the fact that we now have such a dense sampling of the phase space of the Milky Way and the HR diagram that you can start to uncover these very subtle features that are otherwise very difficult to spot. Astrophysical properties for a large number of sources. So we looked just now at basically taking the very fundamental measurements that Gaia itself gives you, the parallaxes, proper motions, colors, and brightnesses, but there is much more. We also provide spectral information and things like metallicities and even alpha element enhancements, all from the low resolution prism spectra in combination with the RVS spectra. And this allows you to do many studies of the galaxy itself, in particular its chromodynamical history. And one of the things that was found on the basis of these low resolution XP prism spectra is by looking at a population of low metallicity red giant branch stars they discovered a core in the center of or a population of stars in the center of the Milky Way at low metallicities that presumably forms one of the very first fragments of the coming together of the Milky Way as a galaxy. So you're really looking at the remnants of the earliest stages of the formation of our own Milky Way. And this is something that you don't get just by having the astrometry and photometry. You need the astrophysical information to tease this out of the data. Another example is up here, where from the low resolution prism spectra, one can actually extract information on the alpha element enhancements of the stars. And this is shown here as alpha versus metallicity in this diagram, where we have the well-known split between the thin and the thick disk, so the older and the younger populations. And although per star these measurements are not particularly reliable because you have so many, you can start to make a statistical distinction between the various stellar populations. And this allows you, for example, as in this work that was done by Akshara Viswanathan for her thesis, to trace the spin-up of the Milky Way disk in the early stages with very low rotation velocity, so coming together of various fragments without much angular momentum, and then later on the buildup of the Milky Way disk, which you can see in the low alpha population spinning up gradually over time as the Milky Way disk becomes more and more rotationally supported. So this allows you then to trace in broad outlines the formation history of our own Milky Way, thanks to the astrophysical information that's also provided as part of the Gaia data. Now then, a final example is that because we have such a large survey which provides both homogeneous astrometry, photometry, but also spectroscopy, you have actually a system to which you can anchor all kinds of other surveys. So many surveys nowadays use Gaia, the sky map of Gaia, both for the astrometric and photometric calibration, and also things like, for example, the Euclid survey relies partly on the Gaia data for their calibrations. And one of the very nice things you can do with Gaia is because the reference frame of Gaia is so precise, that means the stellar reference frame, which you use for the astrometric calibrations, but you can also extrapolate the precision of the reference frame into the future. And this diagram here shows essentially how the precision on the stellar positions degrades as a function of time. This is because of the proper motion uncertainties. And you see the difference between a 5 and a 10-year mission. But what is very interesting is that if you extrapolate this into the past, you end up still with a Gaia catalog, if you track it back 100 years, which is precise at the level of milli-arc seconds or tens of milli-arc seconds, which means that you can take very old photographic plates, for example, recalibrate them astrometrically, and do things like track asteroids in the solar system over a full century or more of data. So this is also a very powerful application of Gaia data as an anchor, as a calibrator for other surveys. Then what will be coming up in the next release, in much more than we have seen before, is that we will have time series measurements for all objects in the Gaia catalog. I'll say a little bit more about that later. But just to remind you, Gaia does simultaneous measurements of the astrometry of stars and their brightness in this part of the focal plane. Then it takes shortly after the prism spectra, and then the radio velocity spectra. And this allows us to have simultaneous astrometry, photometry, spectroscopy. And these time series data, of course, can lead to things like the discovery of Gaia Black Hole 3, which was announced last year, a 30 solar mass black hole in orbit around a normal solar mass star. And in fact, Gaia has uncovered a population of these objects, so 3 black holes so far, but also 20 neutron stars. And many white dwarf candidates. So here are the, I was pointing to the wrong thing. Here are the Gaia neutron star candidates and the black holes. And the special thing here is, of course, that these are very long period objects where normally you need black holes interacting with the star. When you will get time series data for all the objects in the catalog. Okay, So that was the impact that Gaia has on astrometry. And of course, I can come up with many more examples, but I think these in broad outline give you a good impression of why a survey like Gaia, all sky, lots of stars, high precision, is so important for astronomy. Now I wanted to talk about Gaia Unlimited, which is a project that was aimed at providing the Gaia survey selection function, which is needed if you want to dig into a good statistical analysis of the Gaia data, correcting for things like being incomplete at the faint end, etc. So you can find all the information you need at the websites that are listed down here. This is the Gaia Unlimited website itself, but we also provide the tools that we developed as Python code that you can use in your own analyses. And what you see up here is an example of the selection function of the Gaia survey itself. So this shows the completeness of the survey at a magnitude of 20.9. So that's just close to the overall completeness limit of the survey, around 21 or so. And of course, you can see the well-known what you would expect, namely that in dense areas on the sky near the galactic center, Magellanic clouds, the completeness is less because of all the crowding. Around the ecliptic poles, you have high completeness because that's where Gaia scans the sky rather often and quite homogeneously. And then in the ecliptic plane, there's a large variation in completeness because of the variation in the amount of times objects get observed by Gaia. And this is available as electronic tables together with code to handle that. And you can use this in your modeling of the Milky Way to, for example, to take correctly into account the fact that Gaia is complete, but not fully complete as a survey. And you need to worry about those things. I'll make the slides available after the talk so that you have all the links as well that are in the various pages. Okay, just a couple of example applications. So in the project, we also worked on examples of what happens when I combine Gaia with another survey, in this case, the Gaia in combination with Apogee. And we took the Gaia radial velocity sample. So these are a couple of million stars for which from the radial velocity spectrograph, you have good abundances in chemical compositions. And of course, Apogee provides similar information. And what you get with Gaia is near the sun, a very dense sampling again of the phase space because of the very complete nature and all-sky nature of the RVS survey. And of course, Apogee is able to probe much further into the Milky Way disk, where here we have focused on their red clump sample. And what we did is we combined the two samples, and we have here basically a combined selection function or completeness function for the two, and you have the tools available from the GitHub pages to reproduce this. And this allowed us to study the structure of the galactic disk split according to metallicity of the various populations. And one of the things that was noticed in this study is that there is a metallicity-dependent flaring of the alpha pore disk, which you see here in the bottom plot. Now here's an example where we focused on red clump stars in a combination between Gaia and Allwise. So this is now a combination of Gaia and another big photometric survey. And the selection function for these red clump stars is illustrated over in these two plots. So here on the map from above the Milky Way, the color coding indicates the fractional completeness for red clump stars. You can see here the center of the Milky Way, and of course near the sun, we observe many more stars than further away, which is exactly the kind of thing you need to correct for in your analysis of the structure of the Milky Way based on, in this case, on red clump stars. And here's a more sort of visually appealing version of the same thing, and it shows the contour out to which we are about 20% complete in terms of mapping red clump stars. So this sample was used to map out the structure of the disk, including a flared thin disk and a short, thicker disk without a flare in it. And if you look at the residuals of this model, which is the plot over here on the top right, you can notice that the flare of the disk is actually visible in the distribution of the red clump star. So that was not part of the model, hence it shows up in the residuals. And another interesting aspect is that is the plot down here on the top, sorry, on the bottom right. is where you see the residual of the model with respect to the data, and you can clearly see overdensities that look like they are tracing out spiral arms in the distribution of this older stellar population, the red clump stars. And I think this is a very interesting area for further exploration, which we did not do for this paper. Then we also did an analysis of a sample of stars extracted from the XP database, so looking for RGB stars for which metallicities were determined on the basis of the XP spectra. Everything at magnitudes less than 16 with good quality parallaxes. And this was used to basically trace the aurora population, which is again associated with the earliest populations that came together when the Milky Way was forming. And you see over here the all-sky distribution of the sources that we used. And in particular, what you see if you use sources for which you have XP spectra available is that there are areas of the sky where you have much less sources. And this has to do with the fact that in order to publish an XP spectrum, we demanded that at least 15 observations or so were available. And that means that you have very strong selection effects that you need to account for in a sample like this. So in this work, you can read how that was done and how we modeled the aurora population. And down here, you see some comparison with other works and also with work where the population was mapped directly based from a spectroscopic survey, in this case, Apogee, and you have the reference over here. This is a fairly complex model that was employed, and again, you can find the code that we used to do this on the GitHub pages in order to try and reproduce or adapt to your own analysis. Last example of the selection function is that we also looked at the selection function of binary stars. So basically, what we did here is take the trick that is used very often is you look at the renormalized unit weight error, one of the data quality indicators in the Gaia catalog, and you simply say that stars that have a RUA that is above a certain threshold, I assume that they are candidate binary stars, and you can study them, of course, for all their properties. And over here you see a well-known example when you make an HR diagram or a color magnitude diagram and you color code by RUO, or in this case the probability for a star to be selected as a candidate binary. You can clearly see the stars here at the top of the main sequence where you find almost equal mass binaries. Now, if you do this selection, you do get, again, selection effects over the sky, and depending on the threshold that you set on RUE. And what we also studied is what does it mean actually for the underlying population of binaries that you are selecting. So you are sensitive to certain periods and at certain distances, and this is something that you need to take into account, of course, when you do things like trying to infer model parameters for a binary population, for example. And again, you can find everything to reproduce these things on the GitHub pages, and you have the reference to the paper here as well. Okay, that was it for the Gaia selection function tools. And now we switch gears and we have a look at a preview of Gaia DR4. Which will come up at the end of next year and will really be another step change in terms of the Gaia data releases that you have seen so far. So first of all, this is a preview of the astrometric performance of Gaia DR4. So on the left, you see the parallax performance, the median parallax precision in microarc seconds as a function of G-band magnitude, and on the right, you see the performance of for proper motions, in this particular case, the proper motion in declination. I just want to stress these are the actual performances that you will get. So this is not predictions anymore. This is what we know we will have in the catalog next year. So the orange line is Gaia DR3, which is what you have in hand right now. And the thick blue line is Gaia DR4. So you can notice for parallaxes that we achieve what you would expect for a doubling of the time baseline, going from 3 years to 5.5 years. You get about a factor of √2 in improvement over the faint end of the magnitude range. But at the bright end, we do a little bit better, and that's because we have better control over the systematics, as I'll illustrate again just now. And in the proper motions, of course, you see a much larger improvement. That's because the time baseline comes in with a power 1.5 instead of the square root. And that means you get a factor about square root 8 improvement for proper motions, almost a factor of 3. And again, at the bright end, a little bit better improvement because of the better control over systematic errors. This here shows an example of the systematic errors in the various catalogs. So this is what you have right now. So this is an area in the Large Magellanic Cloud where you see the median parallax, well, the residuals with respect to the median parallax. Ideally, of course, this should be a uniform thing because all the stars in the Magellanic Cloud are at the same distance. But you can see a clear spotted pattern, which is indicative of systematic errors in the parallax on small scales in the sky. Now, this middle panel shows you what happens if we take our DR3 astrometric solution code and directly apply it to the new data that we use for DR4, so the 5.5 years of data. And you can see that it actually gets worse. The scale is unfortunately reversed, but you can see that the systematic error levels get larger. And after a lot of work in getting the calibration models, improving them, getting systematics, etc., under control, you end up with this situation, which means that we have much better control now over the systematics. But what I want to illustrate with this is that although we, in principle, do the same thing for DR4 as for DR3 in terms of making an astrometric solution or all the other data processing elements, because we are working on a longer time baseline and we really start again from scratch, you cannot simply apply the old software to the new data. You have to really work hard to get all the calibrations up to speed, up to the level again of making sure that you're actually getting the most out of the increased precision thanks to the longer time baseline. I'll come back to this bottom point later on, the epoch astrometry. Well, maybe I better say something about it now. So one of the brand new data products in Gaia DR4 will be that you will get the epoch astrometry for all sources. So you will get the time series astrometric measurements, which you can, for example, use in your own search for particular types of binary stars or exoplanets, etc. And this here gives you an impression of the precision of the epoch astrometry. So the blue line are the median formal errors on individual astrometric measurements at the CCD level. And the orange line is actually the scatter in the residuals. So the difference between the two are unmodeled errors that are still in there even after the DR4 data processing. So that means that the total uncertainties on the epoch astrometry are limited by the calibration errors to about 80 to 150 microarc seconds. And if you average over the focal plane, you get about 30 to 50 microarc seconds precision on individual measurements of stars. And this, of course, is the important number when you're interested in things like exoplanets. And to give you an impression of what the Gaia DR4 will do for exoplanets, so we are doing a specific effort to look for exoplanets or exoplanet candidates in the Gaia DR4 data processing. And this diagram shows planetary mass and Jupiter masses as a function of semi-major axis. And the blue area is where Gaia will be sensitive. And you see lines for a solar mass star at 200 parsec. Those are the orange lines for DR4 and DR5, and the blue lines are for a low mass star, 0.4 solar masses, closer to us at 25 parsec. But the point that I want to make here is that the exoplanet survey of Gaia is unprecedented. It will do a large survey, about 1 million to 10 million stars, but unbiased across spectral type, age, chemical composition, etc. It will simply look at everything in the neighborhood of the sun. And we expect thousands of giant planets to be uncovered below about 15 Jupiter masses. We cannot go much further than about 1 Jupiter mass. And again, this is around all spectral types from A to M. For a 10-year observation time baseline, this number could triple. So with DR5, you can expect even more. And maybe we will also find many transiting hot Jupiters where in fact in Gaia DR3 there are already two transiting exoplanets that were found with the light curves from the Gaia data. And I think what is the big interest for Gaia is that it's actually sensitive in an area where you can expect to find lots of planets that could be potentially directly imaged because of the long periods up here in the top right of the diagram. Okay, these are examples of the low-resolution prism spectra that we are obtaining at the moment with Gaia DR4. This processing has in fact already finished. And what you see are various spectral types, where the black lines are the prism spectra as derived from the Gaia data, and the orange lines in the background are ground-based high-resolution spectra of standard stars, which we use for example calibrating the photometric passbands. And you can see that there is a very good comparison between what we get from the low-resolution prism spectra and the high-resolution ground-based ones. So again, pointing to increased performance in terms of the photometry. This is also visible in this diagram, where what we show is as a function of G-band magnitude, the precision scaled basically to a single CCD transit. So what you should focus here on primarily is the comparison between the various releases. The green is for DR1, and it goes for DR2, DR3, and then DR4. And what you notice is that especially at the bright end, again, calibration errors are better under control. And so we get closer to what you expect for the photon noise limit, which is indicated by the gray line. Of course, the actual numbers, so here the scaled errors are of the order of 1%. The actual mean magnitude errors, of course, will be much smaller because you have to fold in all the multiple observations that were done over the course of the 5.5 years. Okay, finally, the spectroscopic performance. This is the precision on radial velocities from a comparison to apogee FGK stars. So here's the precision in kilometers per second. This is 1, this is 10 as a function of the magnitude in the RVS band. And note that we will now go down all the way to magnitude 16, so all the way to the survey limit of RVS, where for Gaia DR3 we were still limited to magnitude 13 in terms of radial velocities. And we will have about 250 million radial velocities in the catalog, of which we think 85 million are reliable, so can really be trusted. And that's actually the difference between the red and the blue line, is when you get rid of the unreliable radial velocities, you can see the performance at the faint end is quite a bit better. One example, also coming from the RVS spectra, is that we will also have 7 million line broadening parameters. So basically, which you can interpret as the rotation of the star around its axis, of which, again, a fraction is reliable around 2.6 million. So also in the radial velocities, you will get a very large expansion of the sample. Now, I mentioned before, you will get astrometric time series data. This is also true for the radial velocities. We will give you radial velocity time series for all the sources that were observed. This here is an example of a Cepheid variable, where on top you see the radial velocity variation, and at the bottom you see also the light curve of the star, basically tracing the pulsations of this Cepheid variable, where you have the expected antiphasing of the light curve and the radial velocity time series. And we expect there will be about 650 million reliable epoch radial velocities. So again, a huge data set for you to work with out to magnitude 14. Now you will also get spectra, time series spectra from the radial velocity spectrograph, as well as from the BP and RP prism spectra. And here you see some examples just to prepare you for what's coming of what the epoch spectra look like at the very faint end of the survey. So obviously we will have much better than this for bright stars, which is why we can do things like abundance determinations. But at the very faint end, you see you have signal to noise well below 1. You're transporting a few electrons across the CCD. And so the spectra, of course, will look very noisy. Now, is there anything you can do with this? Yes. If you stack together enough of these spectra, and here you have 6 million faint star spectra combined together, then you can start to notice spectral lines. You can see the three calcium triplet lines very clearly, but you can also see a number of fainter lines in these stacked spectra. And if you compare to a bright star spectrum, you can clearly identify all the different spectral lines in these stacked spectra. So for example, for things like looking for, let's say, diffuse interstellar bands, this could still be interesting to look at these very faint spectra by stacking them together over, say, areas on the sky. Okay, then just on the schedule for Gaia DR4. As I mentioned, it will appear at the end of next year in December of 2026. We announced this already at the EAS before the summer, and that means we're really committed to making this deadline because we have now made that public. And here's just an illustration again of why the data processing for Gaia can take long. Basically, we have the random errors, the blue line, increasing as a function of time, simply because we collect more and more observations, so things become more and more precise. But of course, where you want to be is you want to make sure that the systematic errors are well below the random errors. And this is where all the hard work goes in, not just for the astrometric example that I showed before, but it holds for all the groups working on the Gaia data processing. Is every time you have to really dig again into your calibration models, etc., to make sure that you have your systematics under control. Good. Yeah, this is just one slide again to advertise the fact that next year you will get the time series data for all sources. So this is, and what is also important is that you get about 2.5 billion sources altogether. So we are now publishing everything that we have in our internal working catalog. And this means also a lot of sources where we ourselves say, well, this is maybe not entirely reliable as a source. We're not quite sure. Very few observations, maybe spurious. We will make a very clear distinction. There will be a table of about 2 billion sources that we consider are reliable. This is a normal Gaia source table, but there will be separate tables that provide you also with the sources that we think are less reliable, but maybe there is something scientifically very interesting in there. And the plots over here illustrate again the fact that you will have time series astrometry, radial velocities, light curves, but also the XP spectra and RVS spectra. And then a quick look ahead at Gaia DR5. So Gaia DR5 will be based on 10.5 years of data, so the full extended mission appearing towards the end of 2030. And again, Gaia DR5, like Gaia DR4, will allow for new science to be done. So Gaia DR4 will be a step up because of the time series that you will get for the first time for everything, and Gaia DR5 because of the further doubling of the time baseline. You can look at, for example, compared to what you have now, a factor of 8 improvement in the proper motion precision. And that is, of course, reflected in being able to probe much deeper into the Milky Way in terms of precise samples, which is illustrated in the diagram over here, where for various tracer populations, you can see the limits that you get. Let's say if you're interested in 5% accurate proper motions, the difference between a 5 and a 10-year mission, you get a substantial increase in the volume over which you achieve the same precision. Another thing that is possible with Gaia DR5, we're not yet sure what will exactly come out, but maybe we will be able to put upper limits on very low frequency gravitational waves, so very well below the LISA band, by examining the all-sky astrometry and essentially looking at residuals that might be indicative of the effect of gravitational waves. This is very much to be determined if it's possible. And then down here, I mentioned this already before. If you go from a 5 to a 10-year mission, of course, you expand the periods over which you can find exoplanets. And the period, for example, of Jupiter then becomes accessible because it's the same as the mission lifetime. And we can expect a big expansion again of the number of exoplanets that you find in the Gaia data. Okay, then in the view of time, let me skip quickly through the next step in astrometry, which is to go to the infrared. And the idea is that we would like to pursue an infrared version of the Gaia mission. This was a proposal that was put in for the Voyage 2050 program, and it's actually been selected as one of the candidates for a future L-class mission, not approved yet. but high on the agenda of ESA, so to speak. And this will be an all-sky astrometric, photometric, but also spectroscopic survey in covering everything from the R to the K band. And conservative estimates that we will get at least 15 billion stars in the Milky Way, and of course much more stars now in the disk, the bulge, and the bar, because you can probe through the dust. And we want to go a lot deeper than Gaia and achieve also a better performance. Now, one of the things that you can do with, if you have this Gaia Near mission in the future, say with an epoch of around 2050, and here we are with Gaia around 2020, you can of course combine the two and make very, very precise proper motions at the sub-microarc second per year accuracy level, and of course also do things like discover very long period exoplanets, say around nearby stars. Of course, this has many synergies with other missions, Euclid, Roman, etc. I think one of the powers of Gaia that I pointed to before, the dense sampling of phase space, can now be applied in the infrared to the inner parts of the disk, and of course also the bar and the bulge, and therefore directly link star formation and Milky Way dynamics. And the image in the bottom right shows the increase in the number of stars, the factor more that you get as a function of position on the sky, where of course, especially in the Milky Way disk, we expect orders of magnitude more stars to be visible when you go to the infrared. This here just shows quickly the outline of the focal plane as we foresee it at the moment. The design of the Gaia Near mission will be basically the same as Gaia. So you have here a part where we do the astrometry, and then there is a part where we do broadband photometry, and this is needed in order to characterize the PSF as good as possible with the same level of crowding as you have for the astrometry. And then we are considering to put low-resolution prism spectra back into the design, as well as high-resolution RVS type spectra. And that's because it's been made very clear with the Gaia mission that having the astrophysical information for all the sources at the same time as the astrometry as the astrometry is really essential to the success, to have these astrophysical parameters. And in order to overcome the increased crowding when you go to the infrared, because the PSF of course gets larger, we're exploring now to have a much larger mirror of the order of 3 meters, which possibly could be done by having a segmented mirror, which has of course been demonstrated to work. And the other important aspect is that there is new infrared detector developments which make it possible to do the drift scanning that was done with Gaia, which was up to now only possible with optical detectors. But there are new types of infrared detectors that enable you to do the same kind of drift scanning. And these are infrared detectors where you have a combination of CMOS and avalanche photodiodes, and they really are a game changer in terms of the performance that you can get with Gaia Near. And here you see some comparisons. This is the astrometric performance for a 10-year Gaia mission in terms of proper motion. This is 10, 100, 1 microarc second. And here you see Gaia Near, if you go for 10 years, that mission for a 1.7 meter mirror for different spectral types. And this here is for the much larger 3.4 meter mirror. And you can see that it's almost across the board, except for the very bluest stars. Gaia Near will be a much better mission than Gaia. And this has been really made possible by these new developments in detector technology. Now, Gaia Near, we are, of course, continue to work on the project itself. So, in particular, David Hobbs is coordinating now a white paper that we are putting together to further extend the science case and the design of Gaia Near in preparation for hopefully a full proposal over the coming years towards ESA. And if you're interested to join this effort, we are, of course, very happy to welcome contributions. So just get in touch with me, and I will point you to where you can indicate your interest in the mission. Okay, we're almost there for the presentation. Just one more thing. Of course, as you all know, Gaia ended its observational lifetime earlier this year. On January 15, we stopped the observations, the scientific observations, and we followed up with some technology testing over a couple of months to better understand the Gaia instruments. And then on March 27, there was a very nice ceremony at the Flight Control Center in Darmstadt in Germany, where a lot of us got together to watch Gaia send back its very last signals. You can see here the main control room at Darmstadt, which was used for the event. And here a message that Gaia gave us towards the very end, as the CCDs were one by one switched off. This goodbye appeared. And we also coordinated a ground-based campaign with a lot of amateur astronomers to take pictures of Gaia during this technology testing when it became a lot brighter. And here you can see the track of Gaia over the sky in one example image. They also made a song for Gaia to say goodbye. You can find the link down here. It's, I believe, on the Titanic theme song, but with the adapted text. And that was basically the end of the Gaia space mission. Now, as part of the end of mission activities, we promoted this new Milky Way map, which is based on the Gaia data and all the insights we have gained over the past number of years. It's a very beautiful image, which you can download over here, and I encourage everyone, of course, to use this. And then as a very last slide, just a reminder that the Gaia data is always brought to you by this large consortium of people in Europe working hard to get you the data, but also the great documentation and the archive facilities. So please make sure to credit the team whenever you make use of Gaia data in your scientific discoveries. Okay, I will stop here.
Thank you very much. Great talk. There is, I guess, meant for a lot of questions. So if one would like to start, okay, let's go on. So I think, can you unmute someone? It's there were
Let me check.
hands raised.
Does anyone have questions online? I will unmute you.
I have seen hands, but now I don't see them again.
I saw so many applause, but no questions, it seems.
Okay.
Maybe I can ask the first question. Yeah. The first thing I what are the components of the systematics you mentioned in the Gaia DR4?
What are the components of the systematics?
Yeah, systematics in Gaia DR4. You mentioned the systematics in some fingers, but I don't know. You mean the 0-point files or something else?
Yes. What I was showing was essentially the 0-point variations of the parallax, and how that is now much less than it was before. Yeah. And it still is related to partly to the basic angle variations, but also to all kinds of other aspects that can introduce systematics. And yeah, I think what is important is that the variations are much smaller in DR4, even if the overall 0-point still exists. But that's one number. You can correct for that. But it's especially the variations over the sky with color, brightness, etc., that are better under control for this release. Yeah.
Is there any questions online?
When will be available the near-infrared data? I've seen how many years from now?
Yeah, well, it's part of the Voyage 2050 program, so that already gives a hint of the time scale.
Yes.
But yeah, I think at the very earliest in the 2040s, the launch would take place. And then, of course, we need to observe, we need the data process, etc. So yeah, it's a long time scale, unfortunately.
Long time scale. Yeah. What can we say?
Well, you've seen from the example of Gaia, being able to calibrate data from 100 years ago, that these long time scales in astrometry, yeah, that's part of the game, unfortunately. Yeah.
All of us will be around.
There is online in the window. Could you see it, Anthony?
Yeah, I see the question in the chat. So it says, given that the detection probability in Gaia depends on the apparent magnitude, how does the survey selection function handle stars with large amplitude variability, especially if their magnitude falls near the detection limit? We have not studied this specifically within the Gaia Unlimited project, but yes, this could certainly bias samples of variable stars. And I think there is some work getting underway, in particular for Cepheids, to look at this question of how the sample selection works in the case of variable stars. But yeah, it was not part of the Gaia Unlimited effort.
There is another one.
Gaia Near. So the question is, how far can Gaia Near reach? Can it include the galactic center? Yes, in principle, but the crowding will be in the galactic center for sure, an issue, because of going to the infrared, of course, as I mentioned, the PSF will be wider, and we can compensate partly with the larger mirror. But I think in the very center of the Milky Way, something like Gaia Near would still have issues with crowding. Yeah.
Am I missing someone? Are there any other questions?
Oh, here's the
Another one.
familiar question. What is the price of the Gaia mission by now? I think to give you an overall number, by the end of 2030, when we put out the last data release, the total price will have been of the order of €1.5 billion, so 1.5 billion euros, something like that. But that accounts for 30 years of effort from industry, scientists, etc. Not just the spacecraft itself. So still pretty reasonable at less than €1 per star. So,
Any questions?
Any questions more? Okay.
Maybe I have another one.
If you have another one, I think yes, please.
Because I'm curious in the photometry in the stellar dense field. Because for the area SST, they are confronting some serious problems in the very dense stellar fields. So how do the Gaia collaboration consider the PSF photometry or some other photometry techniques in the stellar dense fields? Yeah, when you handle your data, yeah.
Yeah, so the photometry that comes from the astrometric part of the focal plane, that is PSF photometry that we do. Of course, we have the peculiarity of most data being one-dimensional profiles. But for DR4, we've done a very specific effort of trying to identify cases where you see two peaks in the same image and then doing basically a deblending by fitting them both. The more difficult case is the XP spectra, which is where you get the BP and RP photometry from. Those are, of course, larger on the sky and can more easily overlap. And there, again, for DR4, we've done our best to at least indicate when we think images are blended and the photometry is less trustworthy. And have done some limited experiments at trying to deblend the fluxes as much as possible when you have two sources close to each other. But this is one of the improvements really also for DR5 to get a much better handle on handling these crowded areas with overlapping images. Yeah.
Any others?
Okay.
Okay, I didn't see any raise a hand.
If there are no questions, so we thank very much again. Thank you very much, and let's meet all of you in the next seminar of H1. Thank you very much.
See you next month.
Okay. All right. Goodbye.
Bye.
Bye. Bye.